basically what we have been doing is we are covering the basics of robotics, and then we will proceed to research kind of things in the next week, subsequent weeks. So what you have done is the forward kinematics, inverse kinematics. You have looked at the basic lab. So the lab that we had yesterday and day before is the basic robotics lab. Okay? So using very simple motors, actuators, sensors, you should be able to make very simple devices. Okay? And also robot programming, which you saw, is quite easy. Okay? It's not difficult at all. Okay. So so when you go from here, at least you should be able to control one servo motor using a controller. Okay. So take that as a challenge to yourself. Okay. So the challenge is to yourself, not to us. That before you go from here, you should be able to at least make one 2-link manipulator, do the forward kinematics, inverse kinematics, and control it by yourself. Okay. If you can do it, then you can increase that to 4-link, 5-link, 6-link, it will go on. Okay. So now we are moving on a little bit. I've done forward kinematics, inverse kinematics, trajectory planning. So we are moving on. So we haven't done trajectory planning. So we are moving on to. So we are moving on towards control a little bit. And we saw in the labs that essentially in a robot, we have a link, and then the links are connected in serial chain, and at every joint we have a motor, we have a gear in front, and we have an encoder at the back, right? And this is the motor is controlled from a microcontroller or a PC or whatever. Okay. So essentially, what we are looking at till now is here. And subsequently, we are moving in this direction and trying to see what is there here. Okay, how do you control it? So essentially, what we are seeing is that this is controlled from a PC, which means that you are going to give some voltage to the motor. Okay? And when you give a voltage to the motor, it rotates. So this can be PWM, pulse width modulation, which we are going to give to the motor. The motor is going to rotate, and when the motor shaft rotates, the encoder rotates. This fellow gets position feedback from the encoder. It knows where is the position of this. And based on that, it can control the end effector. But what is important here to note is that our xy here, our xy is the end effector coordinates, whereas this theta1, theta2 are the joint coordinates. So when the motor is rotating, what you're actually controlling is the motor velocities, theta1 dot, theta2 dot, like that. So the motor will be controlling the joint velocities. The joint velocities control will result in the end effector velocity control. So here is x dot and y dot. We are going to control the trajectory of this fellow, okay, in space. That means basically I have to control x and y, different x and y's at different points of this trajectory, so that I can go from here to here, then here, then here, then here, like that. Okay. So this also means that incrementally, if I speak, then this is an incremental velocity in this direction, which is this one. Okay. So in terms of control, we are controlling the joint, and from the joint, we are being able to control the interface. So if I want something desired here, like in the VAL language program, when you saw that when we are saying move P1 or move P2, essentially you are in this space. So you are moving from P1 to P2 or somewhere. So you don't have access to here, right? So what we want to move from P1 to P2, I need to know how to control the joint velocities. So I need to know the relation between this one and that one now. Okay. So from the control point of view, we need to know what is the relationship between the joint velocities and the end effector velocity. Okay. So today, let us look at how can we derive the relationship between these two, and then we will move on to control. How can you control this to finally control that? So now let us again derive it for a 2-link system, a very simple 2-link system, which is easy to understand. So we have only 2 links. So we have 2 links. I call this theta1, and this is my theta2. This is L1. This is L2. This is xy. Okay. This is my x-axis. That's my y-axis. It is just 2 degrees of freedom. 2 axes, one like this and like this are the axis, revolute axis. Now I want to find the relation between this and that. Now from geometry, we can find the relation very easily. So x is equal to, so x is projection on the x-axis, which is this much, which is equal to this much plus that much. X is equal to L1 cos theta1 plus L2 cos theta1 plus theta2. So this is my theta2, this is theta1, this is my theta1, right? So this much is equal to L1 cos theta1, and this is equal to L2 cos theta1 plus theta2, right? So x is equal to L1 cos theta1 plus L2 cos theta1 plus theta2. Okay, from geometry, right? So there is nothing difficult here. From geometry, we can find the relation between x and theta 1, theta 2. Similarly, y, what is y coordinate? Y coordinate is this point here, which is this distance. Now, this distance on the y-axis is equal to this much plus that much. So, this much is equal to L1 sine theta 1, and this one is equal to L2 sine theta 1 plus theta 2. So, y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay. So, we have the relation between x and y on one side and theta 1 and theta 2 on the other side. Right. Now, I want the velocities. Velocity, I mean incremental velocity. So, to get the incremental velocity, I can take the derivative of this. Okay. I can differentiate this side and that side. Now, on the right hand side, we have two variables, theta 1 and theta 2. There are two variables, right? So, I have to differentiate first with respect to this one, then with respect to that one, because there are two variables. So, I will differentiate this side and simply write it as dx is equal to, I will differentiate with respect to theta 1 first. So, there is a theta 1 here and there is a theta 1 there. So, this term here is L1 cos theta 1 and L2 cos theta 1 plus theta 2. Okay, so first I'll differentiate with respect to this and then that, then I'll differentiate with respect to theta 2, which is only that one. So, what I'll get here is minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2 when I differentiate with respect to theta 1, and then when I differentiate with respect to theta 2, I'll be getting minus L2 sine theta 1 theta 2. So, on this side it is d theta 1 and d theta 2. Okay. So, I am writing in matrix form. I am differentiating with respect to theta 1 first. So, I get this theta 1, I get these two terms. Then I differentiate with respect to theta 2. So, theta 2 is only there here. So, I differentiate only this, I get that. Okay. So, the full equation will be dx is equal to this into that minus this into that. Similarly, here I am getting differentiating with respect to cos 1 plus L2 cos 1 2, and this one is becoming L2 cos 1 2. Okay. Is it okay? So, we can write this as dx by dt. I can also write dx by dt, d theta 1 by dt, d theta 1 by dt. Okay. So, essentially I am writing from geometry, I am writing the position relationship, then I am differentiating that and getting the velocity relationship. This velocity is not average velocity, it is not meters per second or something, it is incremental velocity, okay, dx by dt. So, now I get a relationship between the end effector velocity dx and dy and the joint velocities d theta 1 and d theta 2, and it is related by this matrix. So, this is a 2 by 2 matrix, and this matrix is called the Jacobian matrix. Okay. So, this is called the Jacobian. Okay. So, the Jacobian matrix relates the end effector velocity to the joint velocity. Okay. So, in short form, I am writing it here in short form. So, x dot is equal to j into theta dot, okay, where x dot is equal to this matrix, this is equal to that one, and j is my 2 by 2 matrix. Okay, I am writing in short, x dot is equal to j into theta dot. Now, from control point of view, what is required is the joint velocity, which is equal to the j inverse into x dot. Okay. So, what is the objective of doing this? The objective is I want to know what is the joint velocity that I have to give for getting a corresponding end effector velocity, because at the in the world level, when you are writing a program and the robot is doing a task, we are controlling the end effector velocity, not the joint velocity. So, to get a desired joint velocity, to get a desired end effector velocity, what is the corresponding joint velocity comes from this equation, right? So, we have the joint velocity is equal to the inverse of the Jacobian into the end effector velocity. So, this theta dot is equal to inverse of this is adjoint of j divided by the determinant of j into x dot, right. So, the inverse of the Jacobian is equal to the adjoint of j divided by the determinant of j. So, this is how we find the inverse of a square matrix. Okay. So, this is giving us the relation between the end effector velocity and the joint velocity. everybody is understood? This is velocity in the x direction, this velocity in the y direction. So this will have two components, velocity. So if I say a like this, so it will have one velocity component this side, one velocity component that side. Resultant of this will be the resultant here. Right? So this, whatever is the velocity here, it can be broken up into two directions. So if I say it is moving like this, the end effector is moving like this. Okay? It basically means you can decompose that into x and y component. So this is in your x direction, that is in your y direction. Okay, that is x direction, y direction. So three terms here. So first we are differentiating with respect to theta 1. So theta 1 is there here, and theta 1 is there. So this one is becoming minus L1 sine theta 1, this one. This one is becoming, there is theta 1 here. So it's becoming minus L2 sine theta 1 plus theta 2. Now then I am differentiating with respect to theta 2. So theta 2 is not there here, so this term is not there. So there is actually 0 plus. Okay? So this term is not, theta 2 is not here. Theta 2 is only here. So for that, I am getting only one term, which is this one. Okay. Similarly for y also. Okay. Huh? Jacobian is a matrix. Jacobian is the matrix. Yes, so Jacobian is the matrix which relates the end effector velocity with the joint velocity. Okay. So if you are asking what is a Jacobian, then if I am writing an equation of the form, if y is a function of x1, x2, like that, okay, then d of y is equal to, you can write this as d of f into L of, right? You can write it like this, right? So this is the one that will give you the Jacobian, which is giving a partial derivative of all this. I'm interested in dx. Oh, this is not gradient, this is velocity. Because you always have to talk about direction. No? Velocity has to be with reference to a base, with reference to a coordinate system. So this is with reference to this coordinate system. So everything is with reference to this coordinate system. So if you say velocity, then with respect to what coordinate system? You cannot say velocity with respect to just like that without a coordinate system. It is with reference to a direction in space. Now the moment you say direction in space, there is an x and y, right? So this equation itself is based on this axis system. That means the velocity that you are getting is also based on this axis system only, right? Two? Yeah, yeah. No, you can write it directly. Okay. That we'll see. Okay. So now, to answer your question, if you look at what is the meaning of this term, so this term is with respect to zero frame. If you have this vector, okay, this vector is rotating, so it's the cross product term actually with reference to the z-axis. So if this is my E PE, then PE cross ZI is this term. So you can write it also without like this, but this, how this is coming. Okay. It's not fixed. L1, L2 is fixed, but sine theta 1 and theta 2 will change. What is moved? So it depends on theta 2, right? So cos and sine values will start changing, right? So this one, of course, we must have a deeper meaning of this. We'll go along as we go along. Okay, but initially this is the geometrical relationship, this one, and from here we differentiate and we get this, and this matrix is called the Jacobian matrix. Okay. Now essentially, I need to get this. I need to get the joint velocity, which is given by the inverse of the Jacobian matrix into the end effector velocity. Now we see that when we write this J inverse, we get adjoint of J on top and determinant of J at the bottom. So which means that the mapping from here to here, first of all, the mapping from here to here is not a 1:1 mapping. What I mean by that is, if I give a joint velocity of 1 radian per second, it does not mean that the end effector will move by 1 meter per second. That's a 1:1 mapping. Why it is not a 1:1? Because there is a cos and sine terms. And you know that as the angles start changing, this will start changing also. Right? So it means that this map depends on these terms of sine and cos, and that does not make it a 1:1 mapping. Now, the other thing is that in the inverse of this, the determinant of J comes at the bottom. Okay. So which means that if the determinant of J becomes large, okay, then this will become small. Or if this fellow becomes very small, then this fellow will become large. Okay. That means essentially it says that the velocity depends on the value of this one now. Okay. Now velocities we know are also direct, or rather the other way around. The energy is directly proportional to those velocities. If you have higher velocity, you need more energy. If you have lower velocity, you need less energy. Okay. So in terms of energy, if you're talking about the energy consumption of the system, then the larger this one is, the less energy you will take. Right? So if this fellow becomes large, then what will happen is the energy, the torque joint at the joint velocity will become small. Whereas if this becomes small, then this will become large. Now if this fellow were to become 0, then this fellow will become infinity. Right? Now this is not a constant because sine and cos are there. Now depending on where you are in space, the values of theta 1 and theta 2 will change in space. Now if it were to change, then what will happen is this fellow, if it becomes equal to 0, then this will become infinity. So whatever end effector velocity you want, so for that end effector velocity, your joint velocity will go towards infinity or will become infinite. Now a motor cannot give infinite velocity. It cannot go anywhere near infinity also. So it means that if this fellow becomes equal to 0, that kind of a point is basically what we call a singular point. So when we say a singular point, singular points are points at which the determinant of J becomes 0. Okay. So this will mean that at a singular point, your energy requirement will go towards infinity because it is going to infinite velocity. Okay. Is it okay? Now, the converse of this is also true. If this goes towards infinity, then this will start going towards 0. Okay. This fellow can go to 0, or it can become very large. If this becomes very large, then this will become very small. Right? This is the converse. So if I want the least energy consumption, we are talking about energy requirement for a robot, then I should make this fellow large. Right? So one way of answering this question of if I want to do a task and I want to get the minimum energy consumption, then simply I can say that the determinant of J has to be maximized. If determinant is 0, then this term will become infinity. Say that again. No, if this fellow becomes 0, if this becomes 0, then what will happen here? So this will become infinity, right? So whatever velocity you give here will get multiplied by this and it will become infinity. Right? It is independent of what velocity you are giving here. Because anything into this infinite value here will make it infinity now. Where? This one can be anything, right? It can be anything. Anything into infinity is infinity. Right? So this is independent of what velocity this fellow had. Right? So yeah, we are coming to the physical meaning and how we can use it. So this is essentially a very simple way of understanding that the energy requirement is proportional to the value of the determinant of this matrix now. So if this matrix becomes 0, then this will become infinity. Energy requirement is infinity. Whereas if this matrix becomes large, then the energy requirement becomes small. So one way of trying to do a job, do a task, is by trying to maximize this one. Okay? So if you maximize J, then your energy requirement will become minimum. Right? So now this points at determinant of J is equal to 0 is called a singular point. Now obviously it cannot go to a singular point because energy requirement is infinity now. Okay? So it cannot go near there, it can go somewhere near there. It can go near, it cannot go to that point. Now, so that is one understanding. The other understanding is if I maximize this, then the energy requirement will become minimum. Right? So we said that the work volume of a manipulator is this big area. So our work volume is the sphere. So for this 2 degree of freedom manipulator, the work volume is going to become a circle like that. That's the work volume. Our work volume is like this. So you saw in the lab that the robot has a very large work volume. Okay? So if you're trying to answer the question that the work volume is so big, okay, but where should you do a task? Okay, so that the energy requirement is minimum now. Okay, we are trying to answer that question. If the work volume is here, okay, but then this is a 2-link manipulator. I want to do a task. Where should I do the task? Here, 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 here. I should do the task such that the energy requirement is minimum. And how do I answer that? I can simply say that you do the task such that this fellow is maximized. So if determinant of J is maximized, energy is minimized. So that is the place where you should do the task. Right? That's indirect way of saying it. So now when we are trying to say, so one extreme is a singular point where the energy requirement becomes infinity. The other is if I maximize this, the energy requirement will become minimum now. So if I maximize this, then determinant of J, so if I find the determinant of this, okay, so it is this into that minus that into that, determinant of J. Okay. So we find that the determinant of J is equal to, if I want to maximize this, determinant of J is equal to L1, L2 sine 2. We can compute and find that out. So this term into that term minus this term into this term. If you do this multiplication, what we'll find is that it becomes L1, L2 sine 2. Sine 1 gets cancelled. Okay. Why? Because it is of this form. So what we get as the determinant of J, it becomes L1, L2 sine 2. So L1, L2 are link lengths. So you cannot change them. Right? Link lengths are fixed. So the only variable is sine 2 now. Right? So in the determinant, we see that the variable is only sine 2, sine theta 2. Right? So sine theta is theta 2 is the variable. Theta 1 has nothing to do with it. So this is a relationship that says that the joint velocity the joint angle theta 1 has nothing to do with energy requirement. Okay? But it's only joint angle theta 2. Now if you want to maximize sine theta 2, if you want to maximize sine theta 2, what should be the value of theta 2? So for maximize this, get minimum energy. So maximizing this max of sine theta 2. Sine theta 2 is equal to value of 1. So theta 2 is equal to, so theta 2 will be how much? 90 n. See, sine and cos always have two values. So 90 n, 270. Okay. That means if I want to minimize the energy, I have to maximize J. If you have to maximize J, you have to maximize this value. And this value is maximized only if theta 2 is 90 and 270 degrees. That means you should do a task such that this angle is 90 degrees, like this, or like this, such that this angle is 90 degrees. Right? Is it true or it's only just maths? It's only maths. So in robotics, the good part is that there is a lot of maths, okay, but then you have to correlate to the real world because the robot is moving in the real world. It's a mechanism, it's a linkage, right? So it has to correlate to the real world also. Now in our body, we are also a mechanism in some way. Yes, but is it true? So for example, if you see your hand, this is two link. One link, another link. If I see it is planar, if I consider this to be planar without this degree of freedom, then it is one link and another link. It's 2 degrees of freedom, one here, one here. That means when I do a task, if I have to have minimum energy, then this angle should be 90. Is it true? So when you write, you see it's always 90. Okay. So in the beginning few classes, I had said that we always have multiple solutions, but then we have to satisfy this condition of energy requirement. And we all do something in the particular, we walk in the same way, we'll see. That is optimal energy. It is always like this. No, it will change, but you tend to do a task such that you keep this as close to 90 as possible, such that your energy requirement comes down. And your energy requirement comes down because of this condition only. Okay? So when we are writing, for example, we always try to maintain this angle to be 90. So the question of where the robot should do the task is, it should do the task such that this fellow is 90, so it's in this region. Okay? So robot will not do a task like this. It will take a lot of energy. It will not do like this also. It will take more energy. So it will do somewhere here. So when a robot is assembling something, you'll always find that they are doing it in this region of the workspace. Human beings also. So when we are carrying an object or we are doing something, it's in this region. My workspace is from here to there to there to there. This side, here, here, here. But we don't do tasks like this. Okay? Well, you can do, but then your energy will go up. So we always do tasks such that our energy requirement is down. And that will be only in this region. Okay? So although the work volume is here, but the energy requirement is only here. So after fixing the base of the robot, when you are fixing the task, the robot has to do a task, pick and place or whatever assembly, that should be in this region. That should not be here or there. It can do it, but then the energy is going up now. Okay? So whenever a robot is doing, the robot also tends to work in this region only. So human beings also, when we do something, we always tend to, both our hands will always be in this region. You're carrying an object or you're assembling something. Why? Because this angle has to be as close to 90 as possible. Okay? Singularity will be on the boundary. This condition will be in this, in the center part here. Yeah. Yes. Yes. Energy is minimum at 90 degrees. Minimum. Yes. Oh, here, suppose I am giving this velocity 1 meter per second. Okay? X is equal to 1 meter per second, x dot, y dot is equal to 1 meter per second. I need to move with that velocity. Okay? So my end effector velocity is fixed. But depending on where I am in the workspace, this velocity is going to change now. So it will basically mean for getting this one, either I'll get a low angular velocity or I'll get a very high angular velocity. So if you're coming close to a singularity, this fellow is going towards infinity now. So the angular velocity is going towards, is becoming very large number. Now if it becomes very large number, then your energy requirement also is becoming large. From where it will take energy? So whatever, so when you're controlling the motor, you're giving current, right? So your power amplifier is giving current, right? So you have a motor. So in the experiment, what you saw in the lab yesterday, there is a Atmega controller. Then there is a power amplifier like L298. That power amplifier is the one that is supplying the current. Okay. Your PWM is just giving the PWM 0 to 5 volt, but the power or the current is coming from the amplifier. So that amplifier current will start going up now. Yeah, so obviously it cannot go there. It cannot become infinity. It's not possible. So it will go to the higher bound of the motor, and it can't go beyond that, right? But even then, your energy requirement is going up. So you should do the task in such a way that the energy requirement is actually low, right? So what we are controlling here is, see, at the control level, so we have a motor, we have a gear, we have an encoder. This is moving in space with some velocity, tracking some trajectory, which means that we are controlling the velocity of this. Now to control the velocity of this, we have to control the velocity of this also now, right? We are controlling the velocity of the motor now. It is the other way around. To get a desired velocity here, you have to find what is the velocity required here. And the velocity required here depends on this equation now. That means where you are in the workspace, the mapping from here to here will start changing now. So if you're in this region, you'll require a low velocity. If you're in that region or this region, you'll require a high velocity. Velocity where? Velocity here. For the same end effector velocity. The end effector velocity is the same, but the joint velocity is now changing. Encoder is just going to give you position feedback. From that you can get the velocity and accelerations. But what you're actually controlling is motor velocities, right? So when you're controlling the motor velocity is not constant, even if the end effector velocity is constant. That is in open loop control. That is open loop completely. That is not closed loop. So in educational robot, you mean mobile robot? So there you're not controlling, you're not doing any tracking. So you're not controlling any velocity or anything. You're just controlling the direction where it is going. Then you'll need encoder. Then you have to come into all this now. Okay. So just following line, that is again on-off kind of control, right? So there is a completely open loop system, whereas this is a closed loop system. Gear is just to to reduce the speed, because the motor will be going at about 3000 RPM, very high RPM, whereas the joint will be going at much lower RPM, plus to increase the torque. It is independent of theta. It does not matter. It doesn't matter. How can it be? Because it is showing you that. Yeah, so that is the interesting part. As long as you keep this fellow here, you can change this angle to whatever angle you want, and the energy requirement will remain same, because it is independent of theta 1. No, as visualized is something else. So theta 1 is equal to 0 means what? Theta 1 is equal to 0 means like this and like this. So this is the same, this circular fellow. If I draw it along the work volume, so this will be having this circle, if you can imagine, is having another circle. So this full circle is moving like that. So which means theta 1 can vary from 0 to 360 degrees, which means that as long as this fellow is 90, this full circle is moving like this now. So anywhere in this circle, the energy requirement is same. CG, there is no CG in this computation here. So we are simply talking of kinematics. Kinematics has nothing to do with force. To the dynamics of the system. Okay. So this I'm talking only kinematics, not dynamics. After this, we'll have to do dynamics. So it will again depend on your velocity, acceleration, and all those other fellows coming in. Okay. So that is where whether you're in this configuration or you're in this configuration. So the energy requirement will depend on your gravity loading now, right? But this is only from kinematics point of view, that your energy requirement will be minimum if theta 2 is equal to 90 degrees. And that we see actually, because if a system is very slow, to answer your question, if the dynamics is very slow, okay? So dynamics is very slow means acceleration is very, very small. So when you're writing, for example, your acceleration is almost 0. Okay? In that case, it is this one which is governing. So when we are writing, essentially you write with this one equal to 90. Okay. So here we are seeing this term called singularity. So singularity is at a point at which the energy requirements becomes infinity and determinant of J becomes equal to 0. Okay. So here we are saying that singularity is a point where determinant of J is equal to 0. Okay. Which means that the energy requirement is going to infinity. Now, singularities are of two kinds. Singularity can be boundary singularity. So it is at the boundary, or it can be inside, or workspace singularity. So it basically means that the boundary is always singular. Okay. Boundary singularity means if I have two link system like this, okay, then at the boundary it is becoming singular. So boundary singularity means it is becoming singular at the boundary, so this is called a boundary singularity. Inside singularity means there is a singularity inside also. Two-link manipulator does not have a singularity inside. Okay, but 6 degree of freedom or 5 degree of freedom can have a singularity inside also. So for example, in our hand, if I say do like this and you come here, you cannot come. That means although this region is inside the work volume, but you cannot position your end effector here. It means this is singular now. You can go in some other direction, but not like this. Means that you can also have singularities inside. So boundary you have and singularities inside you have. And that happens where determinant of J is equal to 0. Okay. Now, So we also answered the question that if you want to have minimum energy, then you maximize determinant of J. So in terms of a cost function, if you have a robot which is 4 degree of freedom, 5 degree of freedom, or whatever, and we want to do a task, then one way of writing an objective function in optimizing it is you can maximize determinant of J. So choose the values of theta 1 and theta 2 such that this fellow is getting maximized, which means you can take the derivative and look at the gradient. Okay. So in terms of optimization, if you want to perform a task or move this end effector in a particular way such that this fellow gets energy becomes minimum, then we can simply maximize the determinant of J. Okay. Yes. End effector cannot go, or you cannot have a velocity in that. We'll come to it a little bit more in detail. For boundary singularity, here the end effector can go. Okay. So at this point, the end effector can go. Right. Theta 2 is becoming 0. Okay. And sine theta 2 is becoming 0. It can go, but you cannot have a velocity in that direction or this direction. It is like this. You cannot have a velocity in this direction. You cannot move in this direction. It is locked. You can only move in this direction. So which is the direction in which you can have a velocity, because Jacobian relates velocities. Okay. So we have a boundary singularity which is on the boundary. So all robots will have boundary singularity. That means that's the end. And they can have inside also. But now let's move a little bit more. In 2 degree of freedom. 2 degree of freedom, theta 2 equal to 0. Okay, because sine theta 2, na? So wherever that fellow will become 0 is the boundary. Right? So we say the boundary point is a boundary singularity, which means you cannot have a velocity in that direction or this direction. But it does not have a singularity inside the workspace. That it does not have. Okay? But for a larger degree of freedom manipulator, it can also have inside. Say our hand has one inside here. Okay? In this configuration, it is singular. So Puma also can have singularities inside. So when you are trying to do the straight line interpolation, sometimes it can suddenly give error, indicating that it is becoming singular somewhere inside near there. And it cannot, so this question of determinant of J becoming equal to 0, okay, it cannot, energy cannot become infinity. So at most it can go to the maximum that the motor torque is possible, okay, and then it will stop. After that it can't. Infinite is not possible, right? So it is governed by the motor torque also. Okay, so this gives us the important term called singularity. Okay, but we need to understand this a little bit more. Now, what we need to understand is that what is actually happening. Okay, what is the physics of this, or what is going on? Now, in that we are looking at this equation: x dot is equal to j into theta dot, and we said that theta dot is equal to j inverse into x dot. Now this is making the assumption that j is a square matrix, okay, which means it is 2 by 2 or 3 by 3. Now what happens if j is not square matrix? If j is non square, what do I mean by that? Suppose I have one manipulator like this, and I have 3 links now. So theta 1, theta 2, theta 3, xy is xy 2 only. But this is a function of theta 1, theta 2, and theta 3. So your j is going to become 2 into 3. Right? Now it is non-square. Okay? So what is the meaning of this? So it means that we need to understand what is this matrix actually doing. Okay, what is this matrix? So this is essentially of the form, this equation is of the form y is equal to ax. Okay? So this is a linear transform of this nature. So in a transform of this nature, what is this matrix A doing? Okay, that we need to understand. If we need to understand a little bit more of this. Now, what is this matrix actually doing is, if we have this nature y is equal to Ax, what the matrix A is doing, first of all, it is scaling, and number 2, it is rotating. What is it scaling? What is it rotating? Suppose I have my input to be a circle. Okay, this is my circle. This is my input. Then what it is doing is it is rotating the system and also scaling it. What is it scaling? So it is squeezing this fellow like this or stretching it like this. So a circle is becoming an ellipse, and it is rotating the axis system such that if this is my before the axis system before rotation, this is the axis system after rotation. Okay. So what is a linear transform doing of this nature? What is this matrix doing? We are trying to understand the meaning of a matrix now. So this matrix is a transform. What it is doing is it is scaling. What is it scaling? It is pulling it in some direction, and then it is rotating it. So the output is going to become like this, whereas your input was like this. Okay. And this geometry is called elliptic geometry. Okay. Scaling and then rotating. Okay. So we are trying to understand a little bit more about what a matrix does actually. So in that sense, we are trying to understand that this J is a matrix, and this transform is of this nature. We are trying to understand what this means. So it basically means that you are rotating and you are also scaling. That's one. Okay. Now again, let us find a proof of this, okay, because you may not believe it. So the experiment is very easy. First of all, you close your eyes. Don't fall asleep. Okay. You're supposed to close your eyes. Think of a circle. Think of a circle. Okay. You can think of a circle. Now, without opening your eyes, you take your pen on your paper, you draw the circle without opening your eyes. You think of a circle, then you draw the circle. You think of a circle, you can all think of a circle. Then you draw the circle. Come on, do it, quick. What did you get? You won't get a circle. Spiral, maybe if the ends don't meet, then it's a spiral. Because your eyes are closed, the ends may not meet. But what is the shape of that you got? It will be elliptical. It will be elliptical. It will not be a circle. Why? Because the transformation from here to here is governed by this matrix, which is this matrix. And what that matrix is doing is, it is scaling your circle in your head. Okay? And it is also rotating it. And your output at the end of, this is a linkage. Na? So you can think of a circle, but it is going through this process into your linkage. And what output you are getting is this one now. That means this actually takes place. Because this geometry is not governed by 1:1 geometry. This geometry is governed by elliptic geometry. The geometry is different. Okay? So this essentially says that what a matrix does is any linear transform of this nature. This is just an example. Okay? It rotates, it scales, and it rotates. Okay? So you can think of a circle, but then you get an ellipse. Okay? Why? Because of this thing, of this transformation, scaling, and rotation, which is taking place. Okay. Now that this is just to see that okay, this is happening. But let's understand a little bit more now. Now, if you're trying to understand a little bit more as to what, then we need to look at the property of a matrix. Now, when I say matrix, it will mean so a matrix is M into N. A square matrix is only a set of this matrix. Okay. So when I say matrix, it is a non-square matrix. Now, how do you understand what a matrix is doing? We have what we call the singular value decomposition. Okay. So the singular value decomposition, called SVD in short. So if you do SVD of a matrix A, then it is broken up into three matrices, U, sigma, and VT. So if you take the singular value decomposition, SVD is in MATLAB. There's a direct function called SVD. So if you say SVD A, it will give you this matrix into three matrices, U, sigma, and VT. This is called the diagonal matrix, which consists of the singular values, sigma 1 up to sigma n. Other terms are all 0. It's a diagonal matrix. This guy is the orthonormal basis. after rotation. This is the orthonormal basis before rotation. Okay. So if you're trying to understand a matrix, then we have to look at the singular value decomposition of the matrix. Singular value decomposition will give us three matrices, which will break this matrix into three matrices. This matrix is called the diagonal matrix. It's the singular value, which will contain the singular value sigma 1, sigma 2, sigma 3 up to n. This is the axis vectors before rotation. This is the axis vectors after rotation. Okay. Now, those of you in electrical engineering might have done ICP, the principal component analysis, PCA, image processing, signal processing. They always do this. Okay. So when you're trying to look at what a matrix is doing, a transformation, you have to look at the fundamental properties of a matrix, and that is given by these three matrices. This one gives you the singular values. This one gives the basis vectors, means the axis before rotation. This is after rotation. Okay. Now, what is the meaning of singular value decomposition? It basically means dimension reduction. Now, you are used to doing that for what is this dimension reduction? You have been used to doing it for, say, for example, least square fit. So we have data like this. Okay. So you have two dimensions, x and y. So we fit this this line to this group of data and reduce the dimension. How are we reducing the dimension? This has two dimensions, x and y. But we can reduce by fitting a straight line and say there is only one dimension, and this is my principal dimension. Okay. So principal component analysis in image processing, in big data, in all this, they use the same thing. Okay. It basically reduces the dimension and says that you have a lot of data, but this data is dispersed only along particular dimensions. It is not uniformly distributed everywhere. And what are those dimensions? It can be found by doing this one. Okay. So sigma 1 is the maximum value. Sigma n is the minimum value. It will be ordered in that way. So this fellow, the maximum data is along this, is sigma 1. The minimum fellow is sigma n. Okay. Now, if you look in terms of rotation, then this is my input. This is Vt before rotation. After rotation, it comes like this. Okay. So this is my u1 sigma 1, and this one is un sigma n. So sigma 1 is the major axis, is the minor axis. So it's an ellipse. Okay. Now the shape of the ellipse depends on the value of sigma 1 and sigma n. What is n? N is the dimension of your space. So if your manipulator is 10 degree of freedom, so if n is equal to 10, the Jacobian is equal to 6 into 10. Okay. So if you have 10 degree of freedom manipulator, 10 DOF, okay, then it basically means that there are 10 links, 10 degree of freedom. Your Jacobian matrix is 6 into 10 now. Okay. Now if I do singular value decomposition, I'll be getting sigmas. Okay. Now this one will show me the major axis of the ellipse. That means most of the data is in this direction. Okay. The least of the data is in that direction. Okay. This is maximum, minimum, and the other fellows come in between. Now I can't draw because I have only 3D space, whereas this is ND. This is 10D. So we cannot draw 10D. So we simply say 1D, and this is the last one, and the other fellows come in between. Okay. Now this is the mathematical part of it. Now what's very important here is that we are trying to understand the meaning of a transformation y is equal to ax. Okay. What is this matrix doing? This matrix is doing this. But in terms of robotics, what does it mean? It basically means this is the direction of velocity. This is the direction which you can. This is the direction which you cannot move. It is showing a direction in space now. Okay. Yes. Yes. So when you take this one, then this diagonal matrix is ordered such that this is sigma 1, that is sigma n. There can be zeros here. Now, in order to understand this a little bit more clearly, the singular values are the square root of the eigenvalues. Eigenvalues of J transpose. That means when we say eigenvalue, because we are always talking in terms of square matrices, here we end up with non-square matrices. So when you say square matrix, you talk of an eigenvalue. So the singular value is the square root of the eigenvalues of JJ transpose. Why JJ transpose? Because if this is non-square, you do J into J transpose of a non-square matrix, it will become a square matrix. Then you can talk of an eigenvalue. Okay. So this is the square root of the eigenvalues. The rank of a matrix is equal to number of singular values. When we say rank of a matrix, what is the rank of a matrix? Rank of a non-square matrix, okay, also that of a square matrix, is the number of non-zero singular values. Okay. Then what is the determinant of a matrix? The matrix is the product of the singular values, sigma 2, sigma up to sigma n. Okay. Now these definitions are for any matrix, okay, because we are not only talking of square, we are talking of non-square also. So the rank of a matrix is the number of non-zero singular values. The determinant of a matrix is the product of the non-zero singular values, and a singular value is the square root of the eigenvalues of the matrix into its transpose. Okay. Now, if we have a 3 by 2 matrix, okay, what is the maximum rank of that? So we have a matrix which is 3 by 2. What is the maximum rank of that? It can be 2 only. It can be 3. Right? Now, if the rank is the number of non-zero singular values, and if the rank can be only 2, then one of the singular values is 0. Right? You follow? So if it's an m into n matrix, and m is greater than n, then the rank can be only that. And if the rank is n, then m minus n has to be 0 singular values, which means that velocities are not possible in all directions. Okay. Again, you can. This is very, very important. This is extremely important. Okay. Maybe after coming back from tea, we'll have a look at this. This is very, very important because this gives the direction in space in which you can move, and this is the direction in which you cannot move. So when my hand is like this, okay, I cannot have a velocity in this direction. It's not possible, because if I draw the ellipsoid here, the ellipsoid will be like this, which means the major axis is this side, which means I can move like this, but I cannot move like this. Okay, that means although we are saying we have a work volume, but it does not mean that you can move very nicely in every direction. It's not true. Okay? Your energy can go towards infinity, and there are directions which you cannot move. Okay? And this is very, very important for robot manipulation, okay, because you have to worry about the directions of velocity now. So in our hand, if you are like this, you can move like this. You cannot move like this. Right? It's not possible. You cannot have a velocity this side. You're locked. Why? Because in a 2-degree manipulator, the ellipse will vary. If I move this in a straight line, it will start like this. In the center, it will become square. It will become circular. Then it will become ellipse, and at the end, it will become a straight line. Because J depends on theta 1, theta 2. So as it is moving, the shape of this is also changing. The singular values are changing. So it means that when we are somewhere here, I can move like this. In the center, I can move everywhere. And at the end, I can move only like this. Right. So where I can do the task, where I can move the velocities is given by this relationship. Now the more interesting thing is that if velocities are in the real world, forces are also in the real world. That means force and velocity is also related. So if I can move like this, and I cannot move like this, but when I apply a force, I can apply a force like this, but I cannot apply a force like this. They are reverse of each other. That means in the real world, velocity space and force space are orthogonal vectors. So when you push, you always push like this, because you can resist a force like this. But when you're trying to give a velocity, you don't give it like this, you give it like this. Because velocities can come in like this because of this ellipse. So if the velocity vector is this side, okay, this is my velocity vector, which is x dot or y dot, the force vector is this side. They are orthogonal vectors in the real world.